Okay, so in Module 11, we learned about our local neighborhood. We learned about our solar system. In Module 12, we're going to talk about things that are beyond our own solar system. We're going to talk about our own galaxy, the Milky Way galaxy, as well as galaxies beyond. And the reason why this is just, to me, is so very fascinating is because, and why astronomy is so awesome, is because how do we actually learn about these things? We have to study little pinpricks of light, right? You know, we study stars, but what are stars? Just little pieces of light, little pinpricks of light that are so insignificant that we can't even see them during the day. They're out there. We cannot see them, however, because our nearby star, our sun, just completely floods our atmosphere with so much light that those little pinpricks are insignificant. We can't see them. Once the sun goes down, now all of a sudden those little pinpricks start to emerge, but even so, it's not much light. It's not much light. It makes it very difficult to do a lot of stargazing in an urban environment where there's a lot of street lights and stuff. You have to be out in the dark countryside to see a lot of stars. And then what do you do with that information? Astronomy is more than just looking at little patterns in the sky and saying, isn't that nice? Astronomers take those little pieces of light, they gather them with big telescopes. Telescopes are just essentially big buckets for light, just like your eye, right? Your eye gathers light using the pupil, but it's a tiny little hole for light to move into. With telescopes, you want to have big light gathering buckets because you want to gather that light. Then what do you do with it? You use physics. You use physics to tease out all kinds of information. Even though the stars, as you're going to find out, are light years away, it takes years for that light to reach us. When you look at the Big Dipper, for example, the light that you're looking at arriving right now is decades old, in some cases nearly 100 years old. So those objects that are so far away that we'll never be able to travel to them and never be able to do experiments with them directly, we can do it indirectly by using physics. You can tease out so much information. You can find out the mass of that star. You can find out how fast it's spinning. You can find out how fast it's moving away from or toward the Earth. You can find its temperature, its composition. All that information from just a little prick of light. And how's that done? Through physics. Beautiful. If you find yourself getting really interested in learning more about the night sky, I can't encourage you enough to check out any kind of virtual planetarium software. The one that I'm going to demonstrate real quick is one called Stellarium. And Stellarium is a free download. You go to Stellarium, Stellarium.org. It's a free download for the desktop version, a couple of bucks. There is an app version as well. But it's really useful in helping you to understand the motions of the sky and the different skies that are available to you during the course of the year. So let me just first of all demonstrate, I'm viewing from Tupelo, Mississippi. You can actually change your location to wherever you want to go. And you can also change the time, because right now I'm in a daytime sky, and that's not particularly interesting. But there is a way of changing time. You can just move forward in time by hours or minutes or days or weeks if you want, or months. So I'm going to move it into my nighttime sky, and notice once the sun goes down, now I can see those stars. And I can actually add on some things. I can add on constellation lines. I can put on constellation labels. If you really want to, you can put on the art as well. I find that's rather annoying, so I'm going to pull the art off. And the other cool thing you can do is you can actually speed up time. So right now I'm going to stay on my nighttime view, but I'm going to speed things up a little bit. And the nice thing about speeding things up is that it allows me to understand how the stars move during the course of the night. And notice that the stars are all rotating around Polaris. The only star that's not moving in my sky is Polaris. That's what we call the North Celestial Pole. Polaris is always up there. If you live in the Northern Hemisphere, it's always up in your sky, day and night. And the stars are all rotating counterclockwise around that one particular star. That's one of the cool things you can do with Stellarium, is get a better feel for the motion of the stars through the sky during, let's say, one night. Another thing you can do with Stellarium is to get kind of a longer range picture. I'm going to actually kind of slow time down here and change my view. I was looking north, now I'm going to look south. There's my sun. And I want to see I'm going to go ahead and move ahead in time and get into the evening to see my nighttime sky again. This is about 8 o'clock, and I can see certain pretty common constellations. Here's, now again, I'm looking at it. This is October 1st of 2015. I see Sagittarius. I see Capricornus. Looking south, I see Aquarius. So this is what's in my nighttime sky, my evening sky, at this particular time of the year in the fall. But if I advance things several months, notice that in my evening sky is not the ones I just named. I've moved into the spring now. I'm in March, and now I'm seeing. Let's see if we see any common. There's Leo, right? We can see Leo in the nighttime sky. I would see Cancer in my nighttime sky. So notice that the nighttime constellations change during the course of the year. Why is that? Because the Earth is orbiting the Sun, and it's changing its position with respect to the background stars. And that you should have been able to pick up from the diagram in this PowerPoint presentation.
Hi, this is Bob Swanson again, astronomy instructor at ICC, and I wanted to first of all give you a little more explanation as far as the signs of the zodiac. A lot of folks are interested in the signs of the zodiac and really don't understand it. So I wanted to give you a little tour of my classroom because I have the signs of the zodiac in my classroom. I've got them hanging from the ceiling. So if you kind of take a stroll with me, I'll show you that, well, first of all, there's Taurus, and here's Gemini. I've created a little loop on the outside of my classroom. Here's Cancer, flipped around here, and Leo, etc., etc. I've got a little loop that will take you around the outside of my classroom, and I also have 4 signs that are hanging on kind of the inside loop, and those are the the solstices and the equinoxes. So there's the winter solstice, and then I've got the fall equinox, and over there is the summer solstice, and then we have the spring equinox. There it is. So I've got these 2 loops. I've got an outside loop, I've got an inside loop. And I do an activity with my students in my traditional astronomy class where we actually walk around in a circle and we are playing the part of the Earth. And of course the Earth orbits the Sun. So at the center of my circle then is a yellow balloon that represents the Sun. And in addition to orbiting the Sun, of course, what else does the Earth do? The Earth rotates on its axis once a day, once every 24 hours. And so we play the part of the Earth to show not only the motion of the Sun in the sky during the course of one day, but also the motion of the Sun with respect to the background stars over the course of a year. So I'm going to put my camera kind of over here at a distance so you can get a full view of me as well as the Sun. So there's the Sun, and I'll get in position. And so notice the way I do this is I extend my arms. My left arm is my eastern horizon. My right arm is my western horizon. And so therefore I'm going to spin counterclockwise when viewed from above, just like the Earth does. And sure enough, when my left arm is pointed toward the Sun, that's sunrise. And then as I continue to rotate, I'm seeing the Sun. I'm facing the Sun. In fact, the Sun is highest in my sky right now. That's noontime. And I continue to rotate, and sure enough, the Sun, my right arm is pointed toward the Sun. That's sunset. Now it's nighttime. I can't see the Sun. So let me now put you in that, give you a feel for that. So we're going to start out, there's the Sun, okay? And so what's going to happen is you're going to be rotating, your left arm is now pointing toward the Sun. It's sunrise. Where's the Sun? There it is. There's sunrise. The Sun climbs high in your sky, it's noontime. You're continuing to rotate. The Sun is now on your right arm, which is sunset. And we continue around, and it's now nighttime. You can no longer see the Sun. So we rotated one time around, and then sure enough, boom, there's sunrise again. Okay, so you've done one full spin. Okay, that is the rotation of the Earth, that happens in one day. So you see the sun rise, you see the sun climb high in the sky, you see the sun set. Now notice where, with respect to the background stars, was the sun on this particular day. Remember, there's the sun, and if you can look up against my wall there, I've got a sign. In fact, it's Virgo, is the sign that the sun appears to be in line with. And notice that whether it's at daybreak when my left arm was pointed toward the sun, or when my entire body, until I was facing the sun, or when my right arm was facing the sun at sunset, the sun still appeared to be in Virgo. So this particular date, which is mid-September, in fact, I'm right under the fall equinox sign, so that tells me the time of the year that I'm at. So sure enough, if I'm born in mid-September or late September, the sun is in Virgo, not just at daybreak, but during the entire day and at night. See, the sun's in Virgo. When I spin one full time, it's still going to be in Virgo, whether it's daybreak, noontime, and so therefore we would say that my zodiac sign is Virgo. Now I grew up thinking that I was a Libra, but it turns out that I've been a Virgo all this time. So I feel bad for those poor people who have tattoos of their astrological sign, because most likely they're actually off. And the reason being, when those astrological signs were set up, which was thousands of years ago, the Earth's axis was pointed in a different direction. The Earth's axis actually wobbles. It's a period of about 26,000 years, and therefore, since the signs were initially set up, the Earth has wobbled, and therefore the zodiac signs have precessed as well. So I'm actually a Virgo. Now let me show you how this works. That was during the course of one day, and the sun appears to be essentially in Virgo, in line with those background stars, the entire day. But over the course of weeks or months, what happens is I work my way around my classroom. As I continue to spin, I also need to orbit the sun. So over a course of several weeks and months, I wind up over in another part of my classroom. This is about a quarter of the way around. In fact, now I am at the winter solstice. It's December. There's the sun. So notice that you play the same game. The sun can rise when your left arm is pointed toward it. That's noontime, when you're essentially facing the sun. And then as you continue to rotate, now your right arm points toward the sun. That's sunset. And now this is nighttime. And I am seeing an entirely different set of constellations in my nighttime sky. I see Aries, I see Taurus, I see Gemini, I see Orion. Orion is a very, very well-known winter constellation. I don't see it in the summertime because it's in my daytime sky in the summertime. But in the winter, it's in my nighttime sky because of the position of the sun in its orbit around the position of the Earth in its orbit around the sun. But now if I go back to the sun, I see, okay, where is the sun rising right now? Well, it's rising. You can't see these signs way back in the back of my classroom, but it is in line with Scorpius and Ophiuchus. So if you're born in December, you're most likely either a Scorpio or an Ophiuchian. And again, whether it's the sun rising, noontime, sunset, or even at nighttime, the sun is still in Scorpius. It's amongst those background stars. And that's the way the signs of the zodiac work. Again, hopefully that makes it a little more clear. You can play around with the simulation that is part of the Module 3 lab activity. There's a whole thing about the signs of the zodiac. But again, I do this with my traditional classes. We all stand up, we act like the Earth, we spin around, we go around the balloon, around the classroom, just to get a feel for the daily motion of the sun. The sun appears to move from east to west in our sky, and it appears to be stuck amongst the background stars. But that's just over the course of one day. Over the span of several weeks or months, the sun is not stationary with respect to the background stars. The background stars we treat to be stationary. They're so far away. Our sun is not that far away. And therefore it appears to move with respect to those background stars. Why? Because the Earth orbits the sun one full time and 365 days.
Okay, I'm in Stellarium again, and I want to show you a couple of other cool things you can do with Stellarium. First of all, even if you don't change the time, one thing you can always remove is you can always remove the atmosphere. So even during the daytime, you can get rid of the atmosphere. And without the atmosphere, things really improve as far as our viewing. So what I'm going to do is I'm going to swing things around to our northern sky. And hopefully, if you're getting a little more practice, in viewing the night sky, you should be able to find the Big Dipper. And if you're having a hard time, you can put on the lines, and that makes life a little bit easier. And so I can see high in the sky up here is the Big Dipper right now. In fact, I'm going to move time ahead just to swing it around a little more, so it looks a little more like the diagram that you see in the book. Because I wanted to point out the fact that in the book they list the distances to the different stars in the Big Dipper, and we're actually going to use one of the tools in Stellarium to check those distances. And so now we can fully see the Big Dipper. And what you can do is you can actually click on the different stars in the Big Dipper. So again, we've got it in view here. And notice that in the book, they say the tail end of the Big Dipper is 93 light years away. They don't give the name of the star, but the star is called Alkaid. Well, actually, it's more like 100 light years away. The next one is actually a double star called Mizar and Alcor. Mizar is the bigger of the two, and it's about 78 light years away. So notice that the numbers in your book are actually not correct. I'm not exactly sure where those numbers came from. The biggest error, it appears, would be Alioth, the next star in the handle, which turns out to be not 360 light years away, but rather almost 81 light years away. But anyway, again, just because a book has it in there doesn't necessarily mean that it's right. But the cool thing that you should realize is that these stars are really far away, and yet they're relatively close to us. Okay, our nearest star is our sun, and it's how far away? You could put it a couple of different ways. 93 million miles, 1 AU if you wish, or 8.3 light minutes away. The light that we see right now from the sun left the sun 8.3 minutes ago. That's how close our sun is. Notice that these stars that we're talking about in the Big Dipper, the light that is just arriving right now from these stars left almost 100 years ago. For Megrez, 81 light years away. Fad, down at the bottom of the Dipper, 84 light years away. 80 light years away from Merak, and then finally, the farthest one is Dubhe, which is 123 light years away. That means the light that arrives right now actually left 123 years ago. We are seeing that star as it was 123 years ago. Pretty cool. Astronomy allows you to do a little bit of time traveling. In our daily lives, we might associate red as being hot, things that are red hot, and then blue tends to be a color that's more associated with cool things. But in astronomy, it's actually just the opposite. It turns out that when you look at a star, its color is indicative of its surface temperature. And a star is going to produce all kinds of light, as we're going to find out. It produces all kinds of light. It produces radio waves, and it produces microwaves, and it produces infrared waves, and it produces visible light, and it produces ultraviolet and X-rays and gamma rays. But it doesn't produce equal amounts of all these different types of light. And of course, all we see is visible. So it turns out that not all stars produce equal amounts of all the different frequencies of visible light. It turns out that a blue star, a hot star, produces more blue visible light than it does red visible light, and that's why it appears to be blue. It's not that it doesn't produce any red light, it's just the amount of blue it produces compared to red is different. Likewise, with a cool star, it turns out that it produces more in the red wavelengths than it does in the blue wavelengths, and therefore you wind up with a red star. Okay, this skill builder may seem a little intimidating at the outset. When you click this one, you're going to see perhaps some terminology you're not that familiar with. You'll see black body flux and microns and all this kind of stuff. Don't get too involved or focused on that. Just start sliding the slider to change the temperature of this object. And again, we can pretend this object is a star. Forget about black body. We're just going to treat it as a star and see what happens when you create a hot star compared to a cool star. So as you slide the temperature slider, see what impact that has on the graph. The taller the graph, essentially the more energy this star is going to be producing. And the other important thing is for you to realize is that not only is it, it's producing a whole bunch of different types of light. That's why you've got a huge range of different wavelengths that it's producing. But also keep an eye on where the peak of the curve winds up being. You should see that where the peak occurs actually changes as you change the temperature. Now here's a very important distinction, what we call the brightness. It turns out there's two different brightnesses in astronomy. There's apparent brightness, and then there's absolute brightness. We actually call it magnitude. Apparent brightness is just what it sounds like. It's how bright it appears to us. So therefore, what star is the brightest? The sun is easily the brightest star. In fact, it's so bright that in the daytime, it washes out absolutely every other star. You can't see other stars in the daytime because of the sun. But the question is, why does it appear to be so darn bright? Is it because it's truly a really bright star? No, it turns out that our star is actually kind of just an average star, but it's just so honking close. That's why it appears to be so bright. If you bring a candle right up to your eye, it's going to be really almost painfully bright. Not because the candle's super bright, but because it's so darn close. Okay, so that's the difference. We measure a star's brightness two different ways, either apparent brightness or its true brightness. And we can compare the true brightness of other stars with our sun by comparing their what's called luminosity. Luminosity is the true brightness of a star. If we can forget about how close the star is, if we could just put them all side by side, level the playing field, how bright would they appear? That is the luminosity of a star. The HR diagram is going to be a topic of one of your lab activities, and it really is. It's a very important diagram in astronomy because it's a way of plotting the luminosity, the true brightness of a star with its temperature. And when you start doing that for a bunch of stars, you start to notice some trends. You start to notice that a lot of stars fall on kind of a line that goes from upper left to lower right, what's called the main sequence. And notice that our sun is indeed what's considered to be a main sequence star. And it's really just kind of an average main sequence star. It's right almost smack dab in the middle of your diagram there. But there are some stars that don't fall on that main sequence. And you'll see some of those other categories. So spend some time trying to understand the Hertzsprung-Russell diagram as described in your book, because it will be important in doing one of your lab activities today. In Module 11, we talked about the origin of the solar system, the solar nebula theory, and we also talked about the fact that the sun produces energy via nuclear fusion. And it turns out that the sun stays alive by producing energy. By producing energy, it's able to fight off the crushing force of gravity that would cause it to essentially implode. And so it spends most of its life in this nice balance. It produces just enough energy that it's able to stave off the crushing force of the gravity due to its own mass. But of course, as we saw in Module 11, it's constantly turning hydrogen into helium in that process of nuclear fusion. But eventually it will run out of fuel. It'll run out of hydrogen. And things will change. And that's when the death of a star begins. It spends most of its life on the main sequence as a main sequence star. But once it starts running out of its main fuel, then trouble starts to occur because the gravity is still going to crush it, but it's not able to produce enough energy to hold itself up. And therefore it eventually moves off the main sequence into another stage. And usually those stages are much, much shorter periods of the overall star's life. Now, your book doesn't go into this much detail, but I find it relatively interesting. If you look at all the stars on a HR diagram, I'm going to just roughly draw an HR diagram. Remember that HR diagrams are luminosity on the y-axis and temperature on the x-axis, and the main sequence then goes kind of from upper left to lower right. And notice that, remember that your temperature increases going from right to left. So that means that your cool stars are on the right side and your hot stars are on the left side. So what you notice is that on the main sequence, you have some really very luminous hot stars way up in the upper left-hand corner. So I'm going to draw those as blue. So you got, and they're going to be pretty massive too. And then you have what are called red dwarfs down in the lower right-hand corner, which are really small and, again, cool. And because the ones in the upper left are hot and very large, they're going to be very luminous. That makes sense. So they should be pretty high up on the y-axis, whereas your red dwarfs, being small and being cool, should not be very bright at all, and therefore they wind up being at very low luminosities. But the interesting thing is that in order for these hot, massive blue stars to survive, they're huge, right? They're very, very massive, and therefore they're going to have a huge amount of crushing gravity. The gravity just wants to crush them. So therefore, they have to produce a lot of light. They have to produce a lot of energy. And in order to do that, they have to go through a lot of material. And so it's kind of like a gambler in Las Vegas. And so we can compare these two stars. The blue hot star is the really this is the high roller. This is the guy who comes to the table with huge stacks of chips. Whereas the red star, the red dwarf, is one that has just a very, very small stack of chips. The difference between these two gamblers is that the guy who starts out with the big chips, he's also the big risk taker. He puts in huge amounts of chips on every hand, whereas the red dwarf only puts in just the bare minimum. And so therefore, who's going to go through their chips more quickly? It's going to be your high roller. So even though a massive star starts out with a lot more material, in order to keep itself from being crushed, it must chew through that material a lot more quickly than a red star. So therefore, your stars on the upper left-hand part of the main sequence actually have much shorter lives than the stars in the lower right-hand corner of the main sequence. Now our sun, of course, is sort of in the middle. That's a little, it's kind of an average star. Now eventually our star will run out of hydrogen, and it's going to create a little planetary nebula. It's going to shrug off some of its outer material. Eventually it's going to wind up, after going through a red giant phase, it's going to go off the main sequence. Eventually it's going to wind up down over here to the lower left part of the Hertzsprung-Russell diagram as a white dwarf, WD. Those are retired stars. Now think about what a retired person does. A retired person essentially just spends, they're not earning money anymore. They are just spending their life savings. And that's essentially what a white dwarf does. It's no longer technically a star because it's no longer producing light via nuclear fusion. It's no longer producing energy via nuclear fusion. But it is a very hot object, and therefore it will continue to radiate energy just because it's hot. And so it's going to spend a long, long time cooling down. So hopefully the gambling analogy works for you. But white dwarfs are essentially retired stars, spending their savings from a lifetime of earning. The last slide mentioned novas. The Latin word nova is actually for new, because someone would look up in the sky and see a new star that they hadn't seen before. The reason why it was visible, why it was new, was that it was energy that was emanating from a part of the sky where there had been a star, but that star was usually not bright enough to be seen by the naked eye. All of a sudden you have an explosion, and now you can see this new star. So that's true with novas, as well as what are called supernovas. The most massive stars actually collapse. Remember, they spend their whole lives trying to fight off gravity, and they do that by nuclear fusion. And they fuse hydrogen into helium, and the really large stars can actually fuse heavier elements like helium into carbon and oxygen and nitrogen, that sort of thing. But eventually, they can't even fuse those heavier elements. It turns out that iron is the limiting element. but they can no longer produce energy to hold themselves up, and so therefore they have this huge collapse. And the rebound is what's called a supernova. The rebound winds up being an explosion called a supernova, which essentially just tears the star apart. In the process, because it's so energetic, you can actually fuse things like iron into even heavier elements. And it turns out that all the heavy elements that are in your body right now, some of the calcium and magnesium and iron and all that kind of stuff, is from supernova explosions that occurred long in the past. So you really are star stuff. You're made out of elements that were stoked in the furnaces of these very massive stars long ago. Speaking of which, we see one of these actually in our nighttime sky now. Something called the Crab Nebula is actually the leftovers from an explosion of a star that occurred about 1,000 years ago. Chinese astronomers noticed a new star in the sky. And this is just a star that had been just a humdrum star that was barely noticeable, but all of a sudden exploded, and they noticed this bright spot in the sky, which now has started to diffuse, and the leftovers, the guts of that star have now exploded off into space as what's called the Crab Nebula. If you've read in the book about some of the other ends to the life cycles of various stars, you've probably read about neutron stars, and there's also a mention of black hole. But essentially all stars, even white dwarfs, are really dense objects because you're taking the mass, the mass of a star, and by virtue of the fact that its own gravity is going to make it into a smaller thing, it winds up increasing the density. Remember, the density, this is way back from Module 5, is mass divided by volume. So what you're doing is you're taking essentially the mass of a big old star, and the mass really doesn't change too much, but the volume does. As it gets crushed, the volume goes down. So as the volume goes down, the overall fraction winds up going up if we keep the numerator the same. So by decreasing the denominator, the overall fraction increases. So we get really dense objects, neutron stars, or in some cases, a black hole. And a black hole is an object that is so dense and has such a gravitational field, such a strong gravitational field in its immediate vicinity that not even light can escape it. That's why it's called a black hole. If you remember back in Module 11, we were focusing mostly on stuff that was in our immediate neighborhood, our solar system. We were talking about our sun, we were talking about all the other planets that orbit our sun, and all the other stuff that was gravitationally bound to our sun. That's what we call our solar system. But so therefore, when we look out in the night sky, we see a few planets. We see part of our solar system, we see the planets, but then the stars that we see in our night sky are not within our solar system. They are outside our solar system. But as we get farther out, we think about larger and larger distances from our immediate neighborhood, we realize that most of the stars that we see in the night sky are actually relatively close. They're in our what's called Milky Way. They're in a galaxy. So it turns out that our solar system and our sun is just a little star. I'll draw it. So there's our solar system, and our solar system is actually just on one of the spiral arms of a spiral galaxy called the Milky Way. So you remember, there we are. And of course, this Milky Way galaxy is made up of millions, billions of stars. And the galaxy itself is about 100,000 light years across. So all those stars that we saw in the Big Dipper, remember we talked about how far away they were? They were about 100 light years away. Well, they're definitely within the Milky Way galaxy, because the Milky Way galaxy itself is about 100,000 light years across. So everything we see in the night sky is within our own galaxy, with the exception of the Andromeda galaxy. That's the only thing you can see with the naked eye in the night sky that is not within our own galaxy. It is a galaxy unto itself, so that it turns out to be like a little smudge. It's actually the cumulative light of 100 billion stars that we just see as a little smudge in our night sky. Okay, now remember we started this journey by thinking of our Earth with respect to our own solar system, our immediate neighborhood, our sun, our other planets. Remember that our sun is just one relatively insignificant star in the suburbs of the Milky Way galaxy. I just put a little dot there. Now, the Milky Way galaxy seems pretty darn big but until you start thinking about the fact that there are other galaxies, including the Andromeda galaxy. Like I said, that's the only object we can see in the night sky with our naked eye outside of our own galaxy. So what we see in our night sky is all this stuff. We see stars that are in our own galaxy. In fact, ones that are relatively close to where we're located is typically what's in our nighttime sky, with the exception of the Andromeda galaxy, because we see this big old galaxy as just a little smudge in the nighttime sky. This is about 3 million light years away. And of course, the Andromeda galaxy is not alone. There are other galaxies that are within what's called our local group. We have the Large Magellanic Cloud, Small Magellanic Cloud, Andromeda galaxy, etc., etc. But it turns out this is just the tip of the iceberg. There are actually billions and billions and billions of galaxies that make up our known universe. So, remember where we were. We were talking about the Milky Way galaxy and its relation to its own local group. Well, if we start to look even further out, notice that here's our little local group. We're in there somewhere. And it turns out that galaxies are not just uniformly distributed throughout space. They tend to be clustered. So these little dots that you're seeing here are no longer just stars. These are actually galaxies, which means they are collections of billions of stars. So every dot that you see in here is actually billions of stars. Isn't that awesome? Okay, so here's a good place to just kind of catch our breath and think about where we've been and where we are and where we've come from. Let's put it that way. We started out, remember, in Module 11, talking about our Earth and our nearby neighbors, our solar system. And Module 12 is essentially put our solar system in perspective. The fact that we are just an average solar system, a relatively insignificant planet around an average sun. And that sun is in the suburbs of a relatively run-of-the-mill galaxy. And that galaxy is one of among billions of them that are arranged in clusters and superclusters and all that kind of stuff. The question is, how do we know all this? Well, up till about 100 years ago, we didn't know this. In fact, even though astronomers had the appreciation that the sun and the solar system was part of a galaxy called the Milky Way galaxy, a lot of folks thought that was it. And it wasn't until Edwin Hubble came around about 100 years ago that he was able to completely banish that thought, which is really amazing. And so his research helped us realize that there was stuff outside of our own galaxy, including the Andromeda galaxy. We talked about this. This is something that you can see with your naked eye. A lot of folks thought that was just a nebula. They thought it was just a cloud of gas and dust in our own galaxy. Hubble's work determined that that was indeed a galaxy unto itself. And once he discovered that there was a galaxy outside of our own galaxy, then the results started to pour in. As equipment got better telescopes were able to see more and more galaxies farther and farther away. We were able to piece together the picture that the Milky Way galaxy was not the only game in town. Now we talked about the Doppler shift before, the fact that a moving source of waves, whether it's sound waves or light waves, if the source is moving with respect to an observer, the frequency emitted by that source will change. If it's coming toward you, it'll shift to higher frequencies. As it's going away from you, it's going to shift to lower frequencies. That's what's called a red shift or a blue shift. Blue shift is towards higher frequencies. Red shift is away, lower frequencies. What Hubble came to determine was that this is applicable not just to point sources of light like a star, but also for entire galaxies. You can determine the relative motion of an entire galaxy by seeing how much its light is shifting. And first of all, that's pretty huge. And he also determined that the amount of shift, the speed at which the galaxy is moving toward or away, determines the amount of shift. Or you can, vice versa, you can observe the amount of shift and determine how fast the object is moving away. What Hubble discovered was that the farther an object is away from us, the faster it is moving away from us. So the universe is expanding. In fact, the farther away, the greater is the rate of expansion, which is pretty awesome. Okay, the Big Bang Theory. It's a popular TV show. But again, this is something that I wanted to stress in this slide, is that a lot of times the term theory is dismissed because all too often we use it lazily in conversation as just being a guess. As I tried to explain earlier, when I talked about the theory, the solar nebula theory, which is in Module 11, a theory in science explains facts. It explains phenomena, and it also has a predictive capability. So it's an explanatory framework for a lot of things that we observe. And not only does it explain what is observable, but it also can predict other things. And the Big Bang Theory is a perfect example of what a scientific theory is. It's a way, once Hubble had discovered this rate of expansion of the universe and these galaxies, knowing how fast and how far away they are right now, you can essentially pretend that this is a movie, and then instead of letting it run forward, let's wind it backward. And that is the evidence from which the Big Bang Theory was developed. By knowing the rate of expansion of the universe currently and the distances of galaxies from each other, you can run the tape back, and all of the stuff should have come from essentially an explosion 13.7 billion years ago. So, that's a good way. That's one way of explaining what we currently observe. The cool thing is that given that theory, other things should be predictable. And in fact, there's two other lines of evidence that came from that theory. One being what's called cosmic background radiation. And your book does a nice job of explaining the fact that if there was an explosion 13.7 billion years ago, the universe should be at a certain temperature. And that universe at a certain temperature should be emitting electromagnetic radiation at a certain frequency. And sure enough, back in the early 60s, a couple of researchers discovered that radiation that's coming from all directions. So again, the Big Bang Theory predicts that radiation, and sure enough, we have discovered it. The last big piece of evidence that helps to support the Big Bang Theory is the composition of the universe, and the amount of helium that is in the universe is predictable because of the Big Bang Theory. Given what the picture that the Big Bang Theory paints, we would expect a certain concentration of helium in the universe, and sure enough, that's exactly what the concentration is. So the Big Bang Theory is not just a wild guess. It is a framework that explains phenomena as well as predicts other phenomena.